Now, in this video, we are going to take up the discussion on stress-strain relation for the brittle material and other materials. So now to do this, first we are going to have a graph which is the stress to strain, wherein you will not going to find anything else directly. It starts from the origin and it goes to the break point. So that means it is observed from the diagram from the brittle material is that it does not exhibit any yield point. So that is the major criteria. The deviation from stress strain curve from straight line begins very early. So initially in the ductile material where we have a linear line, that is the straight line, it starts from O to P, that is for the proportional limit. But in this case, the straight line begins very early and fracture occurs suddenly at the point B with very small plastic deformation and without necking. So that is the characteristics of the brittle material. The ultimate strength is considered as the failure criterion in brittle materials. Ultimate point and the breaking point are the one and the same. So for examples of this brittle material is the cast iron, the concrete, stone, glass and ceramic materials. Now we go for the stress-strain relationship for the materials including the non-ferrous metals. So here if you see the stress-strain curve, we have for cast aluminium, copper, cast iron, wrought iron, mild steel, nickel chrome steel and high carbon steel. So the stress which has been given for all the basic materials which we are considering for the non-ferrous. The steel and wrought iron proportionality exists almost until the yielding takes place. So that is from both this wrought iron and the mild steel. So when you go for the copper, cast iron, aluminium and higher alloys like nickel chrome steel and high carbon steel, those two are the higher alloys. No clearly defined proportionality limit or the elastic limit or the yield point. The cast iron behaves like a brittle material which fails without any visible elongation or reduction in area. Suppose if you create the stress strain for an aluminium alloy, it exhibits considerably the ductility, though it does not have clearly definable yield point. So that is, this is the one which will going to exhibit the ductility because you have a linear line from O to this point. Then after that it does not have any clear definable yield point. So if you take the stress strain curve for the hard rubber and the soft rubber, here the curve of hard rubber is linear upon up to very large strains. So here it is linear up to a very large strain. So that for up to this point, this is a hard rubber. And then the soft rubber continue to stretch enormously without failure. So it will going to produce, the stretching will going to take place for a larger extent without much failure. Then you have the proof stress. It is the stress necessary to cause non-proportional or permanent extension equal to a defined percentage. So that means you have the proportionality limit and then you have the yield point. From this point you can do, see here here there is a linear stress. So you draw a parallel line to this linear line such that it will going to cut at this point. From this point, you project a line to the stress, so you're going to have 0.2% of proof stress, and here is 0.2% of strain. It is the stress necessary to cause a non-proportional or permanent extension equal to a defined percentage, that is 0.1 to 0.2%. If the specified percentage is 0.2% of the gauge length, the corresponding proof stress is designated as 0.2% of this proof stress. Then the proof stress for a material is determined by drawing a line parallel to the linear portion of the stress strain diagram from a point which is at a distance equal to a specified percentage, 0.2% of the strain on the gauge length. So what is the rupture? It is the stress corresponding to the failure at the point B, or the stress strain diagram or the curve, wherein that will going to be the breaking point or the rupture strength. So what is the percentage elongation and percentage reduction in area? So percentage elongation is defined as the ratio of increase in the gauge length to the original length of the original gauge length expressed in percent. So for percentage of elongation, which will be LF minus L0 by L0 into 100, where LF is the final gauge length at the rupture and L0 is the original gauge length. Now what is the percentage reduction? It is defined as the ratio of maximum change or decrease in cross-sectional area after the fracture of the specimen to the original cross-sectional area expressed in percentage. So what is the percentage reduction in area? Which is A0 minus AF by AF, A0 into 100. So where A0 is the original cross-sectional area of the test specimen and AF is the final area of the cross-sectional area of the specimen. So that is basically because why the final cross-sectional area will always have the reduced diameter, whereas the original cross-sectional area are going to have larger diameter. So larger to smaller one, which has to be divided, taken the reference, and then from there to divide the original cross-sectional area, which is the larger, into 100. So that will going to give you the percentage reduction in area in percent. So what is the working stress on the factor of safety? So when designing machine parts, it is desirable to keep the stress much lower than the maximum or the ultimate stress. And this stress is called the working stress or the permissible stress or design stress or allowable stress. So the ratio of ultimate stress to the working stress will going to give you the factor of safety. The factor of safety is given by ultimate stress by the working stress. For a ductile material where the yield point is clearly defined, the factor of safety is based on the yield stress. What is the factor of safety? Yield stress by the working stress. For brittle material where the yield point is not well defined, the factor of safety is based on the ultimate stress. So whenever you are taking the ductile material, then you can go for the yield stress. If you are going for the brittle material, then you have to go for the ultimate stress. So the factor of safety is ultimate stress by the working stress. So this is how you will be able to analyze the stress strain curve for brittle materials and other materials of both ferrous and non-ferrous. If you like this video, you please subscribe. Thank you.